before this, we are looking to one-dimensional elements. Then we basically from there, okay, we look into linear, one-dimensional element, quadratics, cubic, and we know that linear you need two nodes. There will be two nodes, two shape functions, right? Then we develop what we derive the shape functions up for linear elements. Then quadratic, we need three nodes, three shape functions. Then cubic, four nodes, four shape functions, right? So in today's topic is now from one-dimensional elements, okay, where we look into probably our axial member, beams, frames, all are still in one-dimensional elements. So now, how if we look into two-dimensional elements? Okay, basically it's a surface bodies. Okay, looking into a surface body itself, what will be the available elements that can be used? Okay, then how many nodes they have, then from there we derive out the shape function. So the whole idea or of this topic itself is more towards introduce to you what are the available shape functions. Then that is where ANSYS later on also will have all these types of elements. Then how many nodes are there, and what are their shape functions, and how they are being derived out. Okay, so we are more concerned on this. All right. Okay, so two-dimensional elements. We have the first one, I mean, talking about two-dimensional elements. So if we are having a surface looking into this itself, previously we are looking into just X, right? So we have this, let's say a beam itself, then we are looking into its deformation or deflection about this axial member itself. Then we are not really look into its that particular areas or including the surface itself, right, in the y-axis, right? So in two-dimensional element, probably we can look into this, right? For example, these temperatures, so-called analysis, thermal analysis, temperature itself. So in one-dimensional element, we are only looking into the distribution along the x-axis. But if you are having two-dimensional elements, then you are looking into the temperature distribution or change along this axis as well as this axis. So from here itself, I know what is the x values and what is the y values, right? Then I know what is the temperature at this particular point itself, right? So that two-dimensional element. So here the very common type of element is rectangular elements lah. So here talking about rectangular elements, we have four nodes, right? So later on we have four in terms of if you want to represent this in terms of its shape functions, then you have four shape functions, okay, that related to the nodal temperature at this. Okay, so rectangular, or here we call it a quadrilaterals. So quadratics, quadrilateral elements. Okay, so from rectangular, what we call linear quadrilateral elements. Now we go into quadratic quadrilateral elements, where it's a second orders second orders of so-called functions. So here we have a mid-side nodes, okay, a midpoint nodes in between the two nodes. So again, just similar like what we are having in one-dimensional elements, quadratics functions or quadratics elements, we need three nodes for one this particular line itself. So here total in this case will be 4 plus the mid-side node 4, then we have a total of x nodes. Okay, so we will have eight shape functions later on. Right, then another types that is also common is a triangular element. So also again we have a linear triangular where you have three nodes. So and usually it is represented in the global coordinates compared to just now in quadrilaterals. Okay, we also can be represented in local, global, and even natural coordinates. So can same with this particular quadratic quadrilateral elements. Then we have also linear triangular elements. It can be in natural coordinates, global coordinates, particularly easier to derive or to be used. Then at the same time, we have a second order triangular element, quadratic triangular elements. From 3 nodes now, we have 6 nodes, right? So we will look into one by one of this, how to basically derive the shape functions. So if we have the shape functions, then together with the shape function at that particular nodes, 4 nodes, for example, rectangular or quadrilateral elements, 4 nodes, we have 4 shape functions of at that particular nodes. Then together with the nodal so-called parameters, either temperature, velocities, or whatever deflections, then we can, along that particular the area, or what we call the particular shape itself, we know the distributions, just like what we have previously learned in one dimensional elements. So in any x itself, with the nodal temperatures, okay, with the shape function and the nodal temperature, with the nodal deflection, we can actually predict or approximate the temperature or deflections in making use of the shape function to predict or approximate the deflections or temperature at any point along that particular element itself. So same to 2-dimensional element. Now we have a shape, okay? We have what we call a shape bodies. Then here we are talking about we could approximate, right? Given the x and y positions, then we can actually making use of the shape functions of at the nodes and also the nodal parameters. Okay, then we can predict any points, okay, along that particular shape itself. So making use of the shape functions. So that is important to know what are the shape function of all of these elements. I mean, we have a rectangular or quadrilateral, linear. We have quadratic quadrilateral elements, linear triangular elements, and quadratic triangular elements. So we will look into it. So again, the concepts or the procedure of determining the shape function is still the same. So if you have a rectangular elements, 4 nodes, so you have 4 unknowns, then you can represent your so-called elementary parameters. Here we start with temperatures. So T element is B1 plus B2x plus B3y plus B4xy. Right? So we substitute here. We need we have 4 unknowns, B1 until B4, right? So we need 4 conditions to actually determine our B1 until B4. So of course we have the conditions T equals to Ti. Okay, at this particular point we know that x equal to your local coordinate x equal to 0. So y of course equal to 0 also. Okay, if you look at this coming into here, so your x in local is 0. This is j is L, I and M, this is W. Okay, so we know in local that is the conditions. So we have x equal to 0, y equal to 0 when t equals to Ti, t equals to Tj. We know that at this particular point x equal to L, y equal to 0. Then we have t equal to Tm. At here is x equal to L, y equal to W. Then t equal to Tn at x equal to 0, y equals to W. Okay, so with these 4 conditions, we can solve for these 4 unknown B1 until B4. So this is a similar way of what we have done in one-dimensional elements, or we have also done. Now it involves more unknowns in this case. So we have four conditions to determine the four unknown. So if you substitute all these B1, B2, B3, B4 into here, then we have the TE here is equals to, I think I have, okay, so this is what I have prepared. Okay, so if you this is when x equal to 0, y equal to 0, means substitute into so-called these equations, so-called this equation itself, then we know the B1, we know the B2, we know the B3, and we know the B4. So substitute all this B1 to B4 into, again, these elementary temperatures functions or equations, then and you rearrange it in terms of Ti, Tj, Tm, and Tn, then this itself is our shape functions. Similar like the steps is similar like how we derive in one-dimensional elements. So we have Si, Sj, Sm, and Sn. So these will be our shape functions in here is in local coordinates for a linear rectangular element, or here saying that a linear quadrilateral elements. Okay, so we have four nodes, four shape functions that basically build the what we call elementary temperature or parameter functions. All right. So in the form of matrix, in the form of matrix, of course, you have just now you have here, sorry, you have here Si, we have these T elements, Si, Ti plus Sj, Tj plus Sm, Tm plus Sn, Tn. So in matrix form, of course, you can rewrite at Si, Sj, Sm, Sn. Okay. Here is a 1 times 4, so multiply with 4 times 1, so you have a 1 times 1 functions. Here you have a Ti, Tj, Tm, and Tn, right? So this multiply with this, plus this multiply with this, plus this multiply with this, plus this multiply with this, right? So end up you have a functions of this, okay, this one. All right, so that is in the matrix forms, okay, but of course it's not limited to temperature, as we always mention in one-dimensional element. So it could be any parameters of what variables are unknown variable. So temperature, deflection, velocity, or any that we are willing, or we are trying to solve. Okay, so in this case it could be our deflection in u, okay, u and x-axis, and v in y-axis also can, right? So that is so-called the shape functions Si, Sj, Sm, and Sn, right? So we also can represent just similar like a one-dimensional element. We also can represent in terms of natural coordinates, where here it is represented by this psi, and this is called eta, right? So of course, we know that in natural coordinate, it could be, it is one, the boundary, the limit is upper is 1, then -1, right? The lower bound is a -1, so it's between 1 and -1. The purpose of looking into natural coordinate, because later on in some of the formulations, especially not solid mechanics, talking about thermals, okay, when you formulate, you want to formulate it, a lot of time you need integration. So from 1 to -1, it will be the bound, okay, the limit is 1 to -1 will be easier for the integrations. But here we are using energy method, so we do not have such basically issues. Okay, if we are using the what we call the weight residue methods, then probably you will need this 1 and -1 in this case. Okay, but this how to set your arrangements, so you can put in psi equals to 2x over L minus 1. So we know that when x equal to when x x equals to L, okay, which is at here, this point, we know that our psi equals to 1. When x equals to 0, then we know that our psi equals to -1, right? So we make sure it basically the limit is 1 to -1. Same with this eta when y equals to w, then my eta equals to 1, right? And if my y equals to 0, then my eta equals to -1. Okay, so just substitute into this particular psi and eta, the relationships, into the shape function that we have built just now, right, in the local. Then we will have everything now in a natural coordinate in terms of psi and eta. All right. So if you are having in the node in the midpoint at here, where your x equals to L over 2, your y equals to W over 2, and you can find out that your SI, SJ, here talking about SM and SN will be basically at 0 at this case. Oh, so we know that this is if you are putting this into here, right? So at midpoint itself, you have a x over x. Your x is L over 2, right? Your y is, for example, SI equals to 1 minus L over 2, right? Then here, L over 2 divided by L, then y W over 2 divided by W. Then we have 1 over 2 multiplied by 1 over 2. So our shape function here is 1 over 4. So similarly with this, you can actually see that our shape function here, this is 0, this is 0, then we have a shape function at the midpoint at here, at the center of the, what we call this particular element itself is 1 over 4, right? So all will be the same, equals to 1 over 4, 1 over 4, 1 over 4, 4. Here talking about psi and eta equal to 0, or we are saying that x equals to L over 2, y equals to W over 2. So there is some characteristics over there. So of course, if you are having it still carry the same properties or characteristics that we have previously derived. We're saying that the shape function at let's say node I itself is 1, okay? When it is at I itself is 1, when x equal to 0, shape function is basically 1. But if other than this particular point are all 0, okay, so that is its characteristic or property. It still carry the same thing. So for example, if you have a here you have a negative psi, -1, psi is equal to -1 in this case, then you will have, in this particular case, let's say we are looking into SI itself, we have 1 over 4, and 1 minus 1, right? Then eta is a -1, 1 minus -1 itself. Then basically here you have 2 times 2 is 4, so it's 4 over 4 equals to 1. So the shape function at this particular point itself, SI, shape function at node I, okay, at this particular point is always 1. So if you are talking about SI at node, this particular node itself, so you can see that if you have node J, your SI at this node J is always 0. So SI at node J, okay, at node J, because no relationships at node J itself, where your psi equals to 1, eta equals to -1. If you substitute this into your shape function I, and you know that this psi equals to 1, this will cancel out, become 0, then the whole thing shape function will become 0. right? So in this case, we are saying that it still carry the same property or characteristics of the shape functions. So if you are given a nodal temperatures, here is a nodal stress distributions, as you can see here, okay, using rectangular elements, linear quadrilateral elements, okay. So you have given the nodal stress at here. So we are asked to determine the stress at the center of the element. So probably is at here itself, point 0.125 inch, then here is 0.075 inch. Okay, what is the what we call the stress at the center? So again, uh, we can making use of the shape functions lah. I mean that we have derived just now, right? Then our x here is 0. Just now 0.0125, 0.125. Our y is 0.075, 0.125. Y is 0.075. Then we can determine our si until sn. All right. So then multiplied with our nodal stress itself, right, respectively, with the shape functions of the node or that node itself, we determine the stress at that midpoint is 2083. That is using the local coordinate shape functions lah. So if you're using the natural coordinate shape functions, then yeah, you will also know that your shape function just now we have mentioned that it's 1/4, 1/4, right, at midpoint, right? So substitute this 1/4 multiplied with the nodal stress itself, then we also will get the same results lah, 2083. Right? So that is about linear, rectangular, or quadrilateral elements, right? That is available. Next is quadratic quadrilateral elements. Okay, so it's a egg node, elements. It's basically it's a higher order versions of two-dimensional four nodes quadrilateral elements. Okay, it's of course compared to the linear types, this quadratic one is suitable for curve boundary, right? So it's not limited to just square. So whatever that you have curve, it is better or represented the problem in the curve boundary compared to your so-called a linear quadrilateral element where you only have between two nodes itself you only have one line. Okay, so it have to be a straight line. Even you have a, 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 a curve like that, right? So if you're taking this point and this point itself, it also will consider it as a straight line. So in terms of discretizations, okay, of in terms of you have a curve models, curve boundary, then probably here linear rectangular element is not that suitable. So you can use quadrilateral elements. So here we have 8 unknowns. So if I want to represent in a natural coordinate usually, so okay, then you have the your so-called parameters could be any parameters. Then you have B1 until B8 lah. So in this case, you need 8 conditions to basically come out with the 8 unknown and come out with the shape functions in this case. All right. So what how we can derive the what we call the shape functions here. So we separate into two parts. One is the H point, H node. The second part is the mid side or midpoint nodes. So we start with I, J, M, N. Okay, then followed by the mid nodes, which is K, L, O, P. So this I, J, M, N, this 4 node itself. Okay, we can actually treat these shape functions as a two multiplications of a product of two functions f1 and f2, right? So that the F1, F2 basically it comes with the characteristics of properties. F1, it will, for example, F1 it will produce the value of 0 alongside with the element that a given node that do not have context. Okay, so here we are talking about, for example, I'm taking here is M, okay, for node M itself. So we have to create, let me erase it. For node M itself, okay, the first function, it stated that we need a function that basically give 0 to basically will show 0, okay, only will show 1, okay, at SM when node is M. So that is 1. So other than that, when it's not contact, the line that is not contact, which is at here, at here itself, okay, all the nodes at this particular two line itself will show 0. Okay, so basically this particular function itself basically will suit that particular conditions. So if you are having here your psi is -1, right? -1, right? Then this particular function itself, you have 1 minus -1, this will become 0, then the whole function will become 0. Then your shape function, when you multiply with the 2, this F1, F2, then your shape function will become 0. So that basically fulfill the characteristics how when my shape function at M, my shape function M, okay, at node M, for node J, node I itself, it has to be 0. My shape function at node, my shape function for node M, at node M itself is 1. At the rest, it have to be 0. So this shape function is this function itself, the first shape, the function itself fulfilling these conditions, okay, to eliminate all the nodes, okay, along these two lines. Okay, so we have another function that we have to eliminate this line at this point and this point. This point and this point, the shape functions of SM at this node and this node O and node L also have to be 0. So that comes the second function. Right? So the second function F2, so basically when it multiplied with F1, also it will only produce a value of 1, okay, a unity at this particular node itself, at node M. Other than that, okay, at the neighboring, which is O and L, have to be 0, meaning SM at node M itself is 1. SM at node O, it have to be 0. SM at node L, okay, which is a neighboring along this line, equals to 0 also. So just now the first function, it doesn't consider these two nodes it consider only these two lines, the first function. So it still will show you 1. So we need a second function that actually tell us that when it is at node O, this SM have to be 0. So we need these two functions, multiplication or product of these two functions, to actually tell us to give us the shape function of that particular one node itself. Okay, so it can be represented by, the second function can be represented by basically C1 plus C2 psi plus C3 eta basically. Okay, so in this case we have 3 unknowns, so we need C1, C2 and C3. Okay, so we need 3 so-called condition in this case. So multiplication of these two. So you see, we take one node. Let's say we want to determine the shape function f at M itself. So we take for node M itself, right? We know that for node M itself, our psi is equal to 1, our eta is equal to 1, and we know that SM must be 1. Okay, right? So this is the condition that we have, right? But at the same time, okay, at node O itself, at node O and node L itself, we have the second conditions, okay, that we have at node O itself, we have psi, node O itself is psi equal to 0, right, at here, but our eta is equal to 1, right? We have to, we know that it's not belong to our SM itself have to be 0 in this case, right? Same with this at node L, our psi equals to 1, our eta equal to 0, but our SM equal to 0. So you substitute, we have this condition 1, condition 2, condition 3, right? Based on these three conditions, okay, we substitute into the product of the two functional f1 and f2, right? So you see at these three nodes itself, these three condition itself, this function 1, it won't be 0, it won't be 0, right? You see, either it's 2 or either it's 1, it won't be 0. But if your node is fall under these two line, right, this function 1 will taking care basically, okay? So it will become 0, then the whole shape function will become 0. So for these two node itself, you need the second so-called functions to take care. So here we have three equations, 1, 2, 3. So from here we can find our C1, C2, and C3 making use of these three equations, we can determine the three unknowns C1, C2, C3. Okay. So at the end, our shape function is the functions number 1, okay, which is this one, our f1, and this is our functions number 2. All right. So you can test it if I have a SM. Okay, SMR at node M, of course, is 1. So you can substitute 1, psi equals to 1, eta equals to 1. You will find out that the product of these two function f1 and f2, it will give you our SM equal to 1, right? Other than this, okay, SM at node O, node L, I, J, N, K, and P, which is the other nodes, our SM will become 0 because these two functions will taking care, okay, to make sure it fulfill the so-called the property or the requirements. So here it gives us our so-called the first shape functions, okay, M. Okay, so that is another way of dealing or deriving a shape function of these 8 nodes. Quadratic quadrilateral elements. So that is another example. If I want to look into J itself, right? So again, to make sure J, okay. So we know that the first function have to fulfill that these two line, okay, that is not connected to J, it have to be showing 0. So what we can do is it will be 1 1 plus psi and 1 minus eta basically is from here right? So anything that if you are falling at here, your eta is -1, then your eta is +1, then basically this particular part will become 0, right? Then the whole function 1 becomes 0, the whole shape function will become 0, right? So it take this function basically taking care of these two lines to ensure that all the nodes along these two lines is 0. Okay, so shape function is 0. So at the same time, we have this second shape function to taking care of this K and L. Okay, not K and not L. So we look into J, K, L to determine our C1, C2, C3 for this particular function number 2 in this case. Okay, so our J, when we know that our shape function of at node J is 1, so when your psi equals to 1, eta equals to -1, right? So this is 1 and -1. So the shape function, of course, is f1 multiplied by f2. Okay, so we have 1. Okay, then we have this 1 plus 1, 1 minus -1. So this is our psi, this is our eta, this is our psi, this is our eta. All right, substitute it. So we get our first equation. So at node L, Okay, at node L, we know that our Sj equal to 0. That is, our psi equals to 1, our eta equals to 0. So this at this condition, our Sj is also equal to 0. That come out our second equation. At node K, which is at here, right? We know that our psi equal to 0, our eta equals to -1, right? So that basically our Sj, shape function at J also equal to 0. So substitute, we get the equation number 3. Right, with these three equations, we can get our C1, C2, and C3. Right, so substitute into here, C1, C2, and C3, multiplied together with these first shape functions, first function, 1 plus psi, 1 minus eta, then we have our so-called shape functions of J, node J. All right, so again, it will carry the similar characteristics. So for node J, just now we tried M and J already. So if for node I and node N, it can be derived based on the same methods. So you also get the similar, something similar in this form. Okay. Then for the mid nodes, okay, talking about K, L, O, P itself, then we have another way of deriving it. So for that mid node itself, it have to fulfill certain things. Talking about the first shape functions here, talking about node O, right? We use, let's say, O for example at here, right? So we have again also two functions, but the shape, the first functions, you have to ensure that uh, along this I here not contacting this particular line itself is IN, right? IJ and JM, okay, have to be 0, right? So in this case, we have 1 minus psi, 1 plus eta, 1 plus psi, okay? So it have to be showing that in the case of at here, any nodes at this line, these three lines have to be 0. So we have 1 minus psi. So if I have, let's say, point K, node K at here, we know that our psi is 0, my eta is -1. So when you substitute this 0, okay, this is -1, this is 0, then this thing will become 0, the whole function will become 0, the whole shape function will become 0, right? Of SO will become 0, right? So you are taking care. So because of it have consider these three, when you multiply with it, it's already in terms of quadratic functions. So your C1, it cannot be any functions that is a constant value, basically, because these three, when it multiplies product of these three, is already a quadratic. Then here, the second function C1 have to be a constant values, right? So in this case, we treating, okay, SO at node O, we know that is 1, okay? So at this particular time, our psi is 0, eta is 1. So substitute into our F1, product of F1 and F2, we found out that our C1 is 1 over 2. So at the end, our shape function is 1 over 2, 1 multiplied with these three, F1. This is our F2, which is a constant. This is our F1. Right, so for shape function at the mid node, basically it started with 1 over 2, 1 plus 1 plus eta, 1 minus here is a psi square, or we can remain at the 3 parameters at here. Okay, 1, 2, 3. So for another example, if I'm talking about node L, okay, talking about node L itself, then our first function, we have to taking care of these three lines itself, okay, to ensure that it will become 0 in this case. So we are having here is our psi equal to 1, eta equal to 0, right? So anything be -1, psi equal to -1 have to be 0, and my eta equals to 1 or -1 also have to be equal to 0, because that covering this tree line itself, right? So in this case, that this function itself basically fulfilling to show that the shape function, the function number 1, or eventually the function shape function of L itself have to be 0, because it fulfills these conditions, right? Then in this case, similarly with the second function have to be constant, okay? Then we can determine our constant C1 is also 1/2. Then our shape functions for the mid nodes L itself is 1/2, 1 plus psi, 1 plus eta, 1 minus eta, right? So that basically gives us our shape functions. So at the end of the day, we will have a summary of what you have seen in here, right? So our shape function for the h, I, j, m, n will be 1/4, started with 1/4, okay? Then, yeah, something that you have seen here, okay? Then if you have your mid node one, then that our shape function is 1/2, then you have what you have here differently. Okay, so all of them also follow the same characteristics or properties. At node k, the shape function at k is 1. Okay, at other nodes, okay, at other nodes, my shape function at k is 0. Okay, same with this. At node I, my shape function at I is 1. But at other nodes, okay, my shape function I is 0. So that is basically the characteristics. Another one is S. 1, okay, I mean my total summation or all my shape functions are the addition of my shape function at node I, okay, meaning at node I itself, okay, my Si is 1, the rest is 0, so the totals, okay, of our shape functions summation of all my shape function at that particular node is always 1. So that also is one of the characteristics that we have learned in one-dimensional elements, right? So that is about quadrilaterals. So from 4 nodes to 8 nodes. So now we have here is linear, right? Linear. Next will be the triangular linear triangular. Hold on, let me find. All right. So again, linear triangular, we have 3 nodes. Okay, here is better. Okay, triangular is better suited to approximate curve boundary compared to here talking about quadrilateral or rectangular elements. So if you have a lot of, I mean, your models or whatever your system under analysis is more towards a curve models, curve boundary, than quadrilateral, triangular types of element will be better suited, okay, to approximate our problems, right, rather than quadrilaterals, right? So 3 nodes, okay, so we can represent this in terms of A1, A2, and A3. Then with the 3 condition itself, we can determine our so-called A1, A2, A3. Then we can rearrange everything in terms of shape functions, right? In terms of Ti, Tj, and Tk. Then we can get our shape function Si, Sj, Sk, right? So another way of determining these shape functions. So basically, this is what we have in terms of A1, okay, A2, and A3s. So if you represent this A1, A2, and A3s in terms of TE, just now we have this T element equals to A1 plus A2x plus A3y, right? So this A1, A2, A3 itself, okay, substitute everything in, okay, then you rearrange everything in terms of TI. You see that you have TI, TJ, TK. This is multiplied, this plus multiplied with X, this is multiplied with Y, right? Right. Then rearrange everything in terms of TI, TJ, TK. Then that function itself is SI, SJ, and SK lah. Right. SI multiplied with TI, SJ multiplied with TJ, SK multiplied with TK. Right. So that will be it can be arranged. It's another way is yeah, like what we I have shown here. All right, so we can assume three conditions. Talking about let me refer back to here. So we can at the end here. Let me just show you. So our shape functions basically is if you multiply, expand it, okay, then rearrange in terms of TI, TJ, TK, then our SI is actually 1 over 2A here, talking about alpha I plus beta I X plus delta I Y, right? Where our alpha alpha I itself is equals to xj y k minus x k y j. Okay, then my beta I is equals to y j minus y k. My delta I equals to x k minus xj. Okay, later on I will show you. So if you rearrange everything, then basically it can be represented simplified form in terms of this, okay, the shape functions. So another way of determining this A1, A2, and A3 also, okay, is as shown at here. Okay, so at node I itself, of course, we know that our shape functions are, if I want to determine my shape function at node I itself, shape function of I at node I itself, we know that it have to be 1, okay, right? If I want to know my shape functions, we only need three conditions. If we want to know our shape functions at I, okay, shape function I at node J, okay, we know that it have to be 0, okay, and shape function I at node K also have to be 0. So with these three conditions, we can actually also determine our A1, A2, A3, okay, rather than just now we are using, okay, T equals to Ti, X equal to Xi, Y equal to Yi, T equals to Tj, X equals to Xj, Y equal to Yj, T equals to Tk, X equal to Xk, Y equal to Yk, then give us our three equations, right? These three equations, and to determine our A1, A2, A3 lah, right? So in another case is using the shape function properties. We know that our shape function I equals to 1 at node I, shape function I at node J is 0, shape function I at node K is equal to 0. So from there, we also have three conditions, three equations to solve for these three unknown A1, A2, A3. So you rearrange everything, you know that your A1, where is my A1? A2 is, this is our A3, okay? Okay, and is represented by here. And this, the what we call the denominators of this A3 itself is actually the 2 times my areas. 2 times my area, basically this is the area. Okay, so it's actually a rectangular or a rhombus, rectangular vectors. Okay, it's basically is this area. So that is the proof, okay, of two vectors. I mean, not cross product of the two vectors. That is 2a. If talking about 2a, okay, 2a, which is this is a, this is a. 2a basically is our ab multiplied with my ad. Okay, so if you multiply it, end up you will have this. Okay, which is similar with what you have seen at here, A3. All right, so the denominator of your A3, so it's similar with what you have seen at here. Right, so in matrix forms, okay, if you rearrange it in terms of 1, 1, 1, xi, yi, xj, yj, xk, yk, right, and you find the determinants, okay, also actually give us the 2a, okay, so it also can be uh, validated or verified. This itself, okay, this itself is 2 times the area of these triangular elements, right? So at the end, we will have our A3. Okay, so we can simplify this thing lah. We can simplify this thing equals to 2a, so we don't need to write so long. Okay, it's a 2 times my area of this, but the numerator part of this A3 is xk minus xj. All right, then if I substitute back to this A2 itself, then we have my A3 is x k minus xj divided by 2a, right? Then A2 itself is yj minus yk divided by 2a, and A1, if you substitute back, you will have this xj xjyk minus xkyj over 2a, right? So with this itself, okay, expand it, right? So you will get something similar like what we are having here, right? So at the end, your shape functions can be determined in terms of this. All right. So the shape function Si, Sj, Sk basically is your these parts, okay, multiply with beta x delta y. Okay, all divided by 2a. And we know that it also carry the same characteristics, Si plus Sj plus Sk equals to 1 at any nodes, right? At any nodes. So that is the what we call the shape function of 3 nodes linear triangular elements. So not going to too details on that, but then at least you know how the derivation of a shape function is there. So again, you get the A1, A2, and A3 in this case, right? We have just now determines here. Let me. If we have the A1, A2, and A3 from here, right? So let me see this again. So not to so we have what we have here, okay, A1, A2, A3, right? So you can basically determines your T here, like what you have here lah. Oh, okay, where is it? Sorry. Okay, where is it? So where you are having at here. So we have if you put in TE equals to A1 plus A2 x plus A3 y, right? So that basically give us our so-called the the elemental temperature or any parameters functions in this case, right? So then it will be having in this case this shape functions Si, Sj, and Sk, and you can see that they are basically the same of if you are finding this Si just now, right? So we are having this Si itself is from here, okay? This one is just now we are assuming sorry, here we are assuming Si equal to 1 equals to A1, A2, A3. So once we have find S A1, A2, A3, so our Si is actually equals to A1 plus A2 x plus A3y. So substitute this into its, right? So it's this one, our Si equals to A1, which is plus A2x plus A3y. So we have this xjyk minus xkyj, right? Then divide by 2a plus a2 is y, j minus yk divided by 2a x plus xk minus xj over 2a y. So at the end, you have shape functions as you have seen here, right? So for j also the same, for k also the same. So you repeat that 3 times to get j and k. So that is using the shape function methods, right? If you are using these methods, so not to confuse you. So if you are using these conditions methods, then you will immediately get your A1, A2, A3 like what we have done in quadrilaterals methods and also linear quadrilateral methods, or what we call one-dimensional elements methods. So rearrange everything in Ti, Tj, Tk, then you will have your shape function also the same. So what we are doing this is we try the conditions is different, and we use shape function equal to 1, 0, 0, 3, these three conditions to determine our shape function Si. So we are assuming our Si equals to A1 plus A2 x plus A3y, right? So end up we have this, okay? So it's a similar with not this one, okay? Not this one, but it is similar with what you have here, okay? This one. So that is a linear triangular element. Then in terms of just now in terms of global, right? So in terms of natural, so here we are talking about natural areas, talking about its area coordinates. Here we are again we have psi, eta, and lambda, okay, and lambda itself. So it is you have a so-called conditions of the areas of this triangular triangle. Okay, this triangle is your A3, this triangle is your A1, this triangle is your A2. Okay, so of course, if you are going the entire A itself, if your so-called A1 okay, is your P point is go up to here at this particular point itself, then your A1 is you're talking about here, right? So if your A1 coming, your P coming up to here, so your A1 is the entire triangular, so it's equals to A over A, then it's 1, right? So similar for A2 and A3 and A4. So uh, it is the ratio of your areas, I mean of that particular axis itself. Then the ratio of this, okay, the add ups, okay, again we have these shape functions, right? Si plus sj plus sk equals to 1, right? And the area of a1 over a plus a2 over a, the ratios plus a3 over a also equals to 1. So here we are saying that this is our psi, eta, and lambda itself when they add it is matched to our SI, SJ, and SK lah. Okay, so also it will basically telling us that psi, eta, and lambda, add them up is also equal to 1, is basically equal to my SI, SJ, and SK. Okay, so just now we have the areas A already, right? 2A. So basically divide by 2, we have A. Then A1, of course, you can also find, determine the area of this A1 by along, you will see this, did I share? No, here. So if I want to find A1, so also is given by these things, okay? How you get it, okay? Our A, if we're using matrix form, then we have a 1 over 2, 1, 1, 1, x, I, y, I. Determinant, find the determinants of this x, k, y, k, right? So finding the determinant, then you will get this, okay? Then if you are finding A1s, okay, A1, so it's along A1 is along JK, okay, so along JK, then we have 1, 1, 1, X, Y, X, J, Y, J, X, K, Y, K, right? So finding determinants basically gives A1. Okay, so again our A2, okay, is along IK, right? So here finding the determinant of x, y, x, k, y, k, x, I, y, I, y, I. Then you also will get A3 is along IJ, right? So you have 1, 1, 1, x, y, x, I, y, I, x, j, y, j. Right. So that will basically give us our A3, A2, and A1 if you find the determinant of this matrix, right? Similar with the A. Then you can determine our shape functions. Again, the same lah. Basically, it will end up the same shape function as you have seen here. Okay, SI, SJ, and SK, because this is our psi, this is our eta, this is our lambda. Okay, just that you represent in different coordinate system. Next will be quadratic triangular. Hold on. Next will be what we call quadratic triangular. So again, it's a 6 node. So 6 node, you have 6 unknowns to determine. So if you are putting everything in natural coordinates, here is natural area coordinate again, then these are the shape functions, S, I, J, K, L, M, and N. So, okay. So how it can be determined, it use what we call this Lagrange interpolation functions that we have previously learned in one-dimensional elements. So in this particular case itself, it making use of what we call this. Let me show you this. So in making use of the functions this how to determine I, J, K, which is at the edge, okay? Then we have also the nodes in the mid side nodes or midpoint nodes, which is L, M, and N. So first, basically it represents in terms of layers the order itself, right? So if you are looking into the coordinate itself, so if I'm looking into I itself is when psi equal to 1. So you see or not? This is when psi equal to 1. So it's actually 1. Then the rest lambda and also eta is 0 in this case. So it's 1, 0, 0. But because this is our so-called first orders, basically it say that this is the Lagrange interpolation function. This is the first order. This is the second orders. Okay, the second layer, the second order itself. Then instead of 1, 0, 0, the coordinate they put it 2, 0, 0. Okay, so later on we're making use of this. So if you can name all the coordinates in terms of this case, here at k itself is you are saying that lambda is 1, the rest are 0, so it's 0, 0, 2, okay, which is the second layer. At node j is when your eta is 1, so it's 0, 2, 0, right? So that is first layer. The second layer. The first layer is the mid-side node. Mid-side node, basically, again, you have at this particular point itself, you have you have a value of so-called psi, okay? You have lambda, okay? But your so-called, if you are looking into this, your eta is 0 lah, okay? So this particular line itself. This particular line itself is when your eta equal to 0. When this particular line itself, okay, you can see that this point itself, your psi is 0, right? The rest is 1, 1. And this particular point itself, your lambda is 0, the rest is 1, 1. So you have value. Okay, so making use of this coordinate system that we have determined, then you can putting into this Lagrange interpolation functions to determine our shape functions. Okay, so for example, here, okay, we initially we use, if you still remember, we this is what we have used. If we are talking about node I itself, right? Node I is at here, right? So we have we have if you still remember the what we have learned in one-dimensional elements. Let me recap back in chapter 5. We use these interpolation functions, especially for cubic. So we are saying that if you still remember, let me recap back. Is we are saying that sk equals to the multiplication, all the multiplication of n until m equals to 1, x minus xm, but omitting x minus xk, right? Then we have xk minus xm, right? From 1 to 2, 3 until n, right? But omitting xk minus xk. So if you are making use of this, then we know that our at xi, our psi equals to 1. So making use of this 1 minus at here our so-called our eta is 0, our lambda, I mean here, if you see, you are seeing that this particular line itself, too many lines already. So if you're looking at this line itself, then we have a 0 and we have also half, right? So basically minus 0 minus half. This is minus 0 minus half of psi itself. Then that gives us our so-called shape functions. So the other way that I tell you, based on the coordinate itself, right, that we have determined the 6 coordinate systems, right, with the first layer, first order and second orders. So we can making use of this particular so-called functions or equations to determine the shape function. So our shape function is 1 if my m is 0. Okay, so basically if my m, this is my m, m is 2, m is 0, m is 0. Okay, 2, 0, 0, my m is 0 in this case. Okay, so if it's 0, then this particular shape function is the function itself is 1. Okay, it's 2, then it's more than, larger than or equal to 1, then we have to use these particular functions to determine. Right? So in this particular case, you can see that for SI itself, our coordinate is 2, 0, 0, right? So here we have 0, 0, right? So we've here we use our this the 0, 0, we have to use this when m equal to 0, so it's basically equals to 1, 1. But for non-zero, for m is non-zero, right? So we have to use what we are having here, okay, which is this one. So what it means here is our Rm here is 1 over m, then we have over 2, right? So then we have multiplied with the n, multiplied with psi minus k lah, in this case. So here we have 2n is 2, okay, so 1 over 2, 2 psi, 2 psi, then we minus k. Basically k is from 0 until 2 minus 1 is 1, okay, m minus 1, so that is our k. Okay, so we have psi 2 psi 0 minus 0, 2 psi minus 1. So multiply this function itself, you will get the same like what you have seen using the direct one. Right, this function. So for node L, mid-side nodes, okay, then of course you have 1, 1, 0, right? So it's 0, then it will become 1. So 1, 1 you have to use, because it's larger equal to 1, you have to use these functions lah. Right? So it's 1 over 1, then 1, your n here is two orders, so it's here is 2, your k is 0 in this case, right? So only 0 lah. You don't go up to 1 because it's m is 1, right? So you multiply with it, then you get the shape function at the mid node L is 4 psi eta. Okay, or for node J itself, let's say at this particular point is 0, 2, 0, then you have 0 again is 1, 1, 2 is 1 over 2, then we have 2 eta minus 0, 2 eta minus 1. So end up you have eta 2 eta minus 1 for your shape functions. So end up you have this, right? So this one Si is this, Sk is lambda 2 lambda minus 1, right? So lambda is actually, you see that your psi plus eta plus lambda equals to 1. So lambda equals to 1 minus psi minus eta. So substitute this lambda, then you will get this is your Sk in terms of psi and eta. Okay, so same with Sm and Sn. Okay, so that gives us the shape function for the 4 nodes itself. So if you have a problem like this, okay, making use of triangular elements, then linear triangular elements, then given the nodes, given the nodal temperatures, okay, the position of the nodes, temperatures, right? So you are asked to determine when x equal to 2.15, y equal to 1.1, global, this x is capital, is global coordinates, then what is the temperature values? And also determine the component of temperature gradients. So if you still remember in your test or in your assessment, we are talking about the gradients, right? So gradient, if you have T E equals to S I T I plus S J T J plus S K T K, right? For this particular case, so if we're talking about gradient, then basically it's the dt d basically depends on your x talking about x, or it could be the t. In this particular case, it's got 2 dy. So of course, you can ti is not a function. Si is a function of x and y. So you have the si dx, right? Ti plus the si dx tj and plus. So here we will have the si dy ti plus the si dy tj. So similar like what that day in one dimension elements. So basically you differentiate or the derivative of the shape function itself, you get the multiply with the nodal temperatures or any parameters variables, okay, then you will get the gradients lah. That there is the deflections lah. All right. So here we have this. The third one will be the determine the locations of isotherms, okay, for 70 and 75 degree, because this is a linear, right? So if you are getting 70 degrees, so we can making use of the linear one-dimensional linear shape functions to determine that. So here you have from 69 to 77, we have one point along this line. We have one point is a 70 degree. At here, 67 to 70, we have also at one point here is at 70 degree, right? So along this line, okay, if you're coming down to here along this line itself, right, that is where you get 70 degrees isotherms, okay, 70 degree. So similarly with 75. So later on we can making use of, we have the, you see we have the positions of it, we have the nodal temperature of it, we can actually making use of what we call the linear functions, linear shape functions that we have learned in one-dimensional, okay, element to determine that particular shape functions. All right, so let me show you how it works. So the temperature distribution inside the elements, so you have just taking out what we have, the shape function that we have obtained just now or derived just now, Si, Sj, and Sk, right? So in terms of alpha, beta, and delta, so substitute our given value of x, right? Xj and Xk is already given lah. Here we have the xi, yi, xj, yj, xk, yk, right? And we have this value x and y, okay, which is a 2.15 and 1.1. Then substitute everything in, okay. First the si and si xi, xyi, xj, yj, xk, yk to find our alpha, beta, and delta ijk. Then substitute also to find our 2a, okay. Then substitute our x and y in, okay. Our x and y is point, because now we are having 2.15 and 1.1, so it will lead to the temperature of 69.93. To find our gradient, yeah, basically we find the derivative of our that parameter itself. So in this case, the shape function is actually the derivative of the shape functions lah, because it's a function of x and y, but not the parameters. So in this case, from here, just now our SI, if you are finding the SI, the X itself, then you have the beta, you see not? It will only give us beta I, right? And XJ del SJ del X will get beta J. Del SK del X will get beta K. So here you will have beta I, beta J, and beta K. So if talking about Y itself, del XI, del Y, you have delta I, delta J, and delta K. So that gives us the derivative of gradients of our shape function as well as the temperature in this case. So temperature gradient basically is beta uh, I Ti plus beta J Tj plus beta K dk. Okay, for the x part. For the y part is the delta I di plus delta K J dj plus delta K dk. Okay, so all the value we have already, this one, with together with this di dj dk, we also have already the gradient temperature, the nodal temperature. So we can find the gradient temperatures for x and y in this case. Right. Finally, the what we call the isotherms. So here, if you still remember, we use. Let me find. I cannot find this. Where is it? So if you still remember, we in our shape functions linear in globals, we have our Si equals to xj minus x over L. Okay, then we have xj equal to x minus xi over L. Right. So if I want to find the temperature in between, I have this temperature, I have these temperatures, right? If I want to find our in terms of x or in terms of y, so if I want to find where is the x, okay, at where it gives us 70 degree. So we have our t, okay, t nodes, which is at 70 degree, right? So basically it's equals to my SI. SI here is 77 plus SJ 69, right? So then where we can find where is my X value, right? So again, we have also the Y value, okay? When T equals to 70, right? So my SI is also equals to YJ minus Y over W. Sj equals to Y minus Yi over W, right? So in this case, we also can find our X and so-called Y. So basically is this and this. Or the other way, basically, you are making use of the same, I mean, 77 minus 77 minus 70, 77 minus 69, which is the whole length of this, right, is equal to 1.5 x minus 2.25 and 1.5 minus x that we want to determine. Right, is also equals to in terms of y. In terms of y, then you have a 1 minus y. Okay, that is what we want to determine, and 1 minus 0.75. So here you find your x and y is 2.16 and 0.78. That is only one point at here, right? At the same time, the second the line which is from 67 and 77, you have also at one point you will give 70, which is at here. Okay, so the similar methods you will find your x and y is this, right? So this itself, or this particular line itself, okay, this particular line itself basically give us 70 degree isotherms. For 75 degree, you can refer doing the same things, okay, 77 minus 75, 77 minus 69 for this line, okay, for this particular line. Then you get x and y. Then for this particular line itself, you get x and y, right? So we know that at this particular point itself, right, this particular line itself is where you get a 75 isotherms. All right. Next, we have so-called from basically we have covered all the two-dimensional elements that are available. So you later on you will also see in analysis that you can choose when you are dealing with surface bodies, okay, or 2D analysis. Okay, so we have quadrilaterals, linear and quadratics, and triangular linear and quadratics. So another types here that will help us to optimize our simulations is axis symmetric elements. So this is when you have a three-dimensional problem is symmetrical about an axis. For example, a cylinder itself, right? Then your load is applying along that particular axis itself. Then it is symmetrical. I will say that it's symmetrical about an axis. You have a cylinder types, a circle types of system in three-dimensional, and is symmetrical about an axis. For example, this, okay, is a z-axis. Everything is symmetrical. So, okay, if you are looking into this particular surface, or if you are looking into this particular surface, okay, it's same. So, okay, any surface about that axis giving you the same result. So instead of analyzing the three-dimensionals, you can actually look into a surface or two-dimensionals. So that will save us a lot of times and also computational cost itself. Okay, so again, if you are in this axis symmetrics, okay, later on we will have one example case study that look into axis symmetrics problems. So here we could have this axis symmetric triangular element as well as rectangular element. So it's the same, okay, because in this particular problem we are now in two-dimensionals. Okay, it can be simplified into two-dimensional. So in two-dimensional, then you can either choose triangular or rectangular elements. Okay, so if that is the case, then if you are using triangular elements, of course, three nodes, right? So three nodes, then everything, the shape function will be the same, three shape functions. But in this particular case, your I is not it is represented by Z and R, your Y and X axis. Now it become X, previously X, now replaced by R. Then the Z, previously Y, will become by Z axis. So everything basically will replace, your X will be replaced by R, then your Y will be replaced by the Z. Okay, so that basically gives us our shape function. Everything's still the same, okay, just that the representation of the symbol will be different because now we are in the Z axis and the R axis. Okay, symmetrical. So if you are using quadrilaterals, rectangular elements, four nodes, then we have four shape functions. Again, you have this one in locals, there's four shape function that we have determined. And now if you are using in R axis and Z axis, then in terms of my R itself is our Ri plus X. Okay, our X itself is R minus Ri. Our L is Rj minus Ri, right? Rj, right, minus Ri is, this is our L. Then our Z, again the same. W itself here is Zn minus Zi, right? Then our Z itself is basically Zi plus Y, okay, any number of Y, or Y is actually Z minus Zi. Okay, so all these things, okay, being represented in Z and R, substitute in this X, Y, okay, and W, L, right? So that gives us shape functions that in this so-called axis symmetric axis, okay, dimensions. Okay, here talking about R and Z axis. Right, so everything the same. So if you have this particular cylinders, let's say you have a cylinder, then the nodal temperatures is as you've seen here, okay, IJMN, and you want to know the temperature at you are under axis symmetric, so you want to know the temperature at R equal to 1.2, Z equal to 1.4. So everything in R and Z, then making use of the shape function in R and Z that we have as shown just now, then you can also determine the temperatures. So basically, in terms of your X and Y just now basically you represent everything in terms of R and Z. Right? So you can also determine your temperature. Finally, okay, there is another types of element, we call it isoparametric elements. Right? So this type of elements basically is particularly important in later on our two-dimensional solid mechanic problems or three-dimensional solid mechanic problems. So whereby here it use the shape functions. I'm talking about the shape functions is being used. The same shape function is being used for our parameters. Okay, if you have temperature, so they are using temperatures. Okay, T elemental equals to SI plus if you are having a linear rectangular, so SI TI plus SJ TJ SK TK and SM TM, right? So if you here the parameter is being represented in the shape functions, so the same shape function is also being used for our geometry to express the geometries, okay, X and Y, right? So here they are sharing the same shape functions, right? That is why it called isoparametric elements. Okay, so for example, it's very important in our solid mechanics 2D and 3D problems, and later on we will, when we are in that topic itself, later on in 3D, we will making use of this isoparametric element to formulate our FEA finite element problems in two-dimensional or three-dimensional solid mechanic problem. Okay, so we are making use of these so-called isoparametric elements. So if you have a solid mechanic problem and is the body undergoing a deformations, if you are using quadrilateral elements, okay, four nodes, quadrilateral elements, linear four nodes, then the displacement field with an element, okay, you have a U and V, the displacement in x-axis, displacement in y-axis will be represented by what you have seen here. Right? So in the matrix form, of course, it will become SI, UIX, SJ, UJX, SM, UMX, SN, UMX. So the V part is about the y-axis, okay? SI, UIY, SJ, UJY, SM, UMY, and SN, SN, UNY. Right? So that will be, sorry, it's blocking here. So let me move this up a little bit. All right. So this is the shape function that being used. Then at the same time, okay, the similar shape functions in terms of naturals, we are talking about natural coordinate. The same shape function is being also used to describe the position of any point. So your x and y, I want to describe its position x and y. Also, I can say that it's x xi plus xj plus sm and sn. Right? For y itself is si yi sj yj sm ym and sn yn. Right? So that two the shape functions being used to describe its position as well as parameters. Here is deformations. All right. So later on during formulations, I won't will touch a little bit on this. Let you see how this isoparametric elements works. So later on in two-dimensional, we want to determine using energy methods. We want to determine the strain energies, right? Minimum total strain energies. You still remember? So okay, the strain energy basically is if you refer back to our previous work in Excel when we use energy methods. So our strain energy is okay. Sorry. Right. So our previously we learned that our strain energies is equals to, okay, stress strain over 2 dV, right? Then we put everything in terms of strains, strain square, right? Over 2 dV, and we know that our strain itself is du dx. So we're making use of these informations to find our using minimum total potential energy methods. We find our K U equals to F, right? Our K is basically is the minimum total strain energies, right? If you still remember. So then we have to determine our strains, right? So in the strain in 2D, we have del U, del X, strain in the x-axis. In Y, we have a del V, del Y. Then we have the shear part, shear strain itself is del U, del Y, del V, del X. So if we can determine this del U, del X, del V, del Y, del U, del Y, these are del U, del X, okay, del U, del Y, or del V del X, del V del Y, then we can determine our full strain, then we can determine our strain energies, okay, which is this one, right? Then we can determine our stiffness matrix. Okay, so that is the whole idea, right? So in the case of our shape functions, so is as you have seen the displacement field as you have seen here, U and V is equivalent to this. So we're taking the derivative itself. Basically, we can actually find this del U del X, del V del Y, del U del Y, del V del X, right? We can actually relate it to that del U del X, this particular derivative that we want that relate to strains, okay? So if we can find strains, we can find the strain energy, then we can relate it to elemental stiffness matrix of 2D and 3D problem later on. So uh, so if you can find the derivative with respect to x and y, then we can find, okay? If your shape function is expressed in terms of psi and eta in natural coordinates, so that is what we have, okay? What we have derived previously. So if you can determine your probably del, let's say here is u, okay? Del u, uh, del u, here del psi, right? Then you have basically we can use making use of the chain rules. Okay, we can have del. Let's say we use a parameters del these parameter functions over del x. Okay, and del x over del psi. Okay, plus del the functions. Okay, any now it can be the displacement del y, then del y, del psi. Okay, so that basically represent this. Okay, so our intentions is we want to find this part. Okay, this part is the one that relate to the strings. Okay, x y y, because this is del so-called u del u, let's say del x del y, right? So all these values, okay, that is related to this. So using this chain rule, we can make it split it out lah. Oh, then you can see that this particular part is actually, this particular part is, we have this Si Sj, then M and N, right? So, and if my S is in terms of natural coordinates, psi and eta, right? So del psi basically is this particular part, right? Then this is we do not have, and we know that our x and y, x or the default our position x and y is also represented by si xi plus sj xj, right? Then SIYI plus SJYJ, right? So this XS is also represented in terms of a function of psi and eta, right? So if I can find the derivative dx, the psi, dx, the eta, dy, d psi, dy, d eta from these two, right? So then we have this particular part, right? So if I have this, if I have this derivative, sorry, I use the other color. If I have this derivative from the position functions, then at the same time, we have these two derivatives from these parameter functions here, displacement field functions, right? Then we can determine our derivative with respect to x and y in this case. So you rearrange everything, okay, in terms of matrix forms. So it can be represented by, as you have seen here. So this itself, we call it as a J matrix or Jacobian matrix, right? So it rearrange everything. This if multiplied with a J inverse, this multiplied with a J pre-multiplication of J inverse, this thing become I. So we can determine these particular parts. Okay, so this basically related to what we want, del u, del x, del u, del y, del v, del x, del v, del y. Okay, so with this itself is what we have, the inverse matrix of this, right? And this itself is the matrix for the derivative of our displacement field, okay, with respect to the natural coordinates, psi and eta. Then yeah, we can find this. With this, we can find the strains. With the strain, we can find the strain energy. With the strain energy, we can find the elemental stiffness matrix. Right, so later on, we will look into this when we are touching on the two-dimensional and three-dimensional solid mechanics problems, okay, where we derive this equation further to determine basically the stiffness matrix, the load matrix, and the full entire Ku minus Ku equals to F, okay, equations. Okay, using these isoparametric elements. All right, so just to summarize a little bit, so two-dimensional element, we have two types, okay, rectangular and triangular. So we have two orders, up to two orders, linear and quadratics. So we have linear, rectangular. Here we are having four nodes, okay. So we have the shape function, four shape functions. Then we are deriving in local and natural coordinates, okay, particularly more useful in natural coordinates. So quadratic quadrilateral element is also a rectangular types, but second orders quadratic. So we have from four nodes linear, we have 8 nodes in quadratics. So we have 8 shape functions. Okay, so these are the shape functions that we just now have also touched a bit on how to derive it out for the 8 nodes. Okay, then we have linear triangular, okay, and represented in it could be represented in our global coordinates and natural coordinates also, psi, eta, and lambda, right? So this is the 3 nodes, 3 shape functions that we have discussed just now. Then followed by that is also triangular, but it's higher order, second orders, okay, 6 nodes. Then we have 6 shape functions, right? I, J, K, and L, M, N, right? So these are all the shape functions in terms of its natural coordinates, psi, eta, and lambda.